When we look up at the night sky, it feels calm. The stars appear fixed, the planets move slowly, space seems quiet. But that calm is an illusion. All around us, ancient rocks are moving, silently, endlessly, circling the sun at tremendous speeds. They are called asteroids. Most of them will never touch Earth. Most of them will never be seen. And yet, without them, planets, including our own, would not exist. Asteroids are older than Earth. They formed before oceans, before continents, before life itself. They are fragments of the earliest solar system, preserved in space like fossils drifting through time. For most of human history, we noticed them only when they burned through our sky as shooting stars or struck the ground as mysterious stones. We feared them, we worshipped them, we misunderstood them. Today, science has revealed something extraordinary. Asteroids are not just threats from space, they are the raw ingredients of worlds. They carry water, metals, and organic molecules. They record the violent history of planet formation. They have shaped Earth's surface, rewritten life's history, and may one day shape humanity's future beyond Earth. Every asteroid is a message from the past, traveling billions of years to reach us. In this video, we will follow these ancient objects from their birth in a collapsing cloud of dust, through collisions and chaos, to their role in creating and sometimes destroying life on Earth. We will explore what asteroids are made of, how they move, why they matter, and how humanity is learning to live with them and even protect itself from them. Because asteroids are not outsiders, they are part of our story. And when we understand them, we understand something deeper about ourselves and about the kind of universe we live in. When we hear the word asteroid, most of us imagine a disaster, a giant rock racing toward Earth, a sudden explosion, an extinction-level event. But that image hides a much deeper truth. Asteroids are not invaders from space. They are ancient residents of our solar system. They have been here since the very beginning. An asteroid is a small, rocky, or metallic body that orbits the sun. Unlike planets, asteroids are too small for gravity to pull them into a spherical shape. They remain irregular, jagged, and uneven, frozen in their original forms. In scientific terms, asteroids are leftover building blocks from planet formation. They are not failed comets, they are not debris from destroyed planets, they are pieces of the original solar system that never changed. To understand asteroids, we must first clear up some confusion. A meteoroid is a small fragment of rock moving through space. When a meteoroid enters Earth's atmosphere and burns, it becomes a meteor, the streak of light we call a shooting star. If any part of that object survives and reaches the ground, it is called a meteorite. Asteroids are the parent bodies. They are the source of most meteoroids and meteorites we find on Earth. For most of human history, this idea was unthinkable. Ancient cultures believed stones falling from the sky were supernatural signs. Some were worshipped, others were feared. Even early scientists refused to believe rocks could come from space. The idea seemed impossible. How could stones fall from the sky when there are no stones in the sky? They asked. It was not ignorance, it was a lack of context. In the late 18th century, reports of meteorite falls became too numerous to ignore. Scientists finally accepted that Earth is constantly interacting with material from space. This realization changed everything. But asteroids themselves remained hidden. They are small, they reflect little light, and space is vast. The first asteroid was discovered in 1801 by Giuseppe Piazzi. He was searching for a missing planet between Mars and Jupiter, a gap predicted by mathematical patterns of the time. What he found instead was a small moving object. It was named Ceres. At first, Ceres was classified as a planet, but soon more objects were found in similar orbits. It became clear that this was not a single world, but a population. The asteroid belt had been discovered. This discovery forced astronomers to rethink how planets form. Why were there thousands of rocky bodies between Mars and Jupiter? Why did none of them become a planet? Asteroids were not accidents, they were evidence. They told the story of a solar system that formed through chaos, collision, and gravity. And perhaps most importantly, asteroids matter because they preserve the past. Planets are active. They melt, recycle, and erase their early history. Earth's surface is constantly reshaped by geology, erosion, and life. Asteroids are different. Most have remained unchanged for 4.6 billion years. They are time capsules, holding the original materials from which planets were built. Some contain water-bearing minerals. Some contain complex organic molecules. Some contain metals formed in the cores of long-lost planetary bodies. When we study asteroids, we are not just studying rocks, we are studying the raw ingredients of worlds. Every planet, including Earth, was built from material like this. Every atom in our bodies was once part of an ancient object orbiting a young sun. Asteroids are reminders. They remind us that planets are not permanent. They remind us that creation and destruction are linked. And they remind us that our story began long before Earth existed. Asteroids did not become planets, but without them, planets and life could not exist. And now that we understand what asteroids are, the next question becomes inevitable. Where did they come from? To answer that, we must travel back in time, to the birth of the solar system itself. To understand where asteroids come from, we must travel back in time, not millions of years, not even hundreds of millions. We must go back 4.6 billion years, to a time before Earth, before the planets, before the sun itself took its final form. The solar system began as a vast cold cloud of gas and dust drifting through space. This cloud, called the solar nebula, was made mostly of hydrogen and helium, with small amounts of heavier elements forged in earlier generations of stars. At some point, something disturbed this cloud. Perhaps a nearby supernova shockwave passed through it. Perhaps gravity simply took over. The cloud began to collapse. As it collapsed, it started to spin. Most of the material fell toward the center, forming a growing, heating core, the young sun. The remaining material flattened into a rotating disk around it. This disk was not smooth. It was turbulent, chaotic, and filled with dust grains smaller than a grain of sand. At first, these particles drifted silently. Then they began to stick. Electrostatic forces caused dust grains to cling together. Gentle collisions allowed tiny clumps to grow into larger aggregates, millimeters, then centimeters, then meters across. This stage was fragile. Many growing bodies were destroyed as often as they formed, but some survived. Over time, gravity took over. Once objects reached a few kilometers in size, their gravity became strong enough to pull in nearby material. These bodies are called planetesimals, the direct ancestors of asteroids and planets. The solar system was now a crowded construction site. Planetesimals collided constantly. Some merged, growing larger. Others shattered, sending fragments spinning away. In regions closer to the sun, lighter materials were vaporized, only rock and metal survived. Farther out, ice and volatile compounds could exist, allowing different kinds of bodies to form. Asteroids formed across this disk, but their fate depended on where they lived. Between Mars and Jupiter, something unusual happened. Jupiter began to grow. As it accumulated mass, Jupiter's gravity became immense. It stirred the surrounding region, increasing collision speeds and preventing planetesimals from merging into a single planet. Instead of building, they broke, again and again. This region became what we now call the main asteroid belt. Asteroids here are not fragments of a destroyed planet. That idea was once popular, but it is wrong. There was never a planet here. Jupiter's gravitational influence made sure of that. Asteroids are survivors of a process that never finished. They are the building blocks that never found a final home. Radiometric dating of meteorites confirms this story. Many asteroids formed at the same time as the Sun, making them older than Earth itself. Some were heated and differentiated, forming metallic cores and rocky mantles. Others remained primitive, preserving water, carbon, and organic molecules. When these bodies later broke apart, they scattered fragments across the solar system. Some of those fragments eventually reached Earth. When we hold a meteorite in our hands, we are holding material that formed before our planet existed. Asteroids are not leftovers in the sense of waste. They are archives. They record the earliest chemistry, temperatures, and dynamics of the solar system. They tell us how chaos slowly became order and how gravity decided which worlds would grow and which would remain small. Asteroids exist because planet formation is not perfect. It is violent, it is inefficient, and it leaves behind evidence. In that evidence, we find our origins. Now that we know how asteroids were born, the next step is to understand what they are actually made of, because not all asteroids are the same. Some are dark and carbon-rich, some are rocky and reflective, some are dense and metallic. To explore that diversity, we move to classification. Now that we understand where asteroids come from, we can begin to understand what they are made of. At first glance, asteroids may seem like simple rocks drifting through space, but in reality, they are incredibly diverse. Each asteroid carries a chemical fingerprint, a record of the conditions under which it formed and the history it experienced. To organize this diversity, scientists classify asteroids based on how they reflect light, their spectra, and the meteorites they produce. The largest and most common group is known as C-type asteroids. The C stands for carbon. C-type asteroids are dark, primitive, and rich in carbon-based compounds. They reflect very little sunlight, which makes them difficult to observe. These asteroids contain water-bearing minerals, organic molecules, and some of the most ancient material in the solar system. Many scientists believe that objects like these delivered water and organic compounds to the early Earth. In other words, C-type asteroids may have helped make life possible. Next are S-type asteroids. The S stands for silicate. These asteroids are brighter and more reflective than C-types. They are made primarily of silicate minerals mixed with nickel-iron metal. S-type asteroids are more common in the inner regions of the asteroid belt, closer to the Sun, where higher temperatures shaped their composition. Many of the meteorites found on Earth, especially stony meteorites, originate from S-type asteroids. Then there are M-type asteroids. The M stands for metal. These asteroids are rich in iron and nickel and are much denser than other types. Some are thought to be fragments of the metallic cores of larger bodies that were shattered by massive collisions early in the solar system's history. If so, M-type asteroids give us a rare glimpse into the interiors of ancient planetary bodies. Beyond these main categories, scientists have identified many subtypes. Some asteroids are unusually red, indicating complex organic compounds. Others show signs of hydrated minerals, suggesting past interaction with water. A few asteroids blur the line between asteroids and comets, showing weak activity or releasing dust. This diversity tells us something important. Asteroids did not all form under the same conditions. Some formed hot and dry. Some formed cold and icy. Some were melted and differentiated. Others remained untouched. Another critical distinction is internal structure. Some asteroids are solid monolithic rocks. Others are known as rubble tiles, loose collections of fragments held together by gravity. Rubble pile asteroids formed after collisions shattered larger bodies. Instead of dispersing completely, the fragments slowly reassembled into irregular, porous objects. These asteroids have low density and can be surprisingly fragile. Understanding this structure is essential, especially when considering asteroid deflection or impact risk. An asteroid's composition determines how it reacts to force. A solid rock behaves very differently from a loosely bound pile of debris. Asteroids also vary dramatically in shape. Because they are small, their gravity is weak. This allows them to retain sharp edges, deep craters, and bizarre shapes that planets cannot. Some asteroids resemble potatoes. Others look like dumbbells or spinning tops. A few even have small moons orbiting them. Every asteroid is a geological record. By studying their composition, structure, and shape, scientists reconstruct the early solar system piece by piece. Asteroids are not random. They are organized by physics, chemistry, and history. And now that we know what kinds of asteroids exist, the next logical question becomes, where exactly are they located? Because asteroids are not scattered evenly through space, they occupy specific regions shaped by gravity, motion, and time. Asteroids do not wander the solar system at random. Their locations are shaped by gravity, orbital motion, and long-term stability. To understand asteroids fully, we must understand where they live and why they live there. The largest population of asteroids resides in a region between Mars and Jupiter known as the main asteroid belt. This belt is not a dense field of rocks packed closely together. On average, asteroids in the belt are separated by millions of kilometers. Yet, collectively, they form a vast structured population. The belt exists where planet formation was disrupted. Jupiter's immense gravity prevented material in this region from combining into a planet. Instead, countless rocky bodies remained locked in orbit around the Sun. Within the asteroid belt, patterns emerge. Some regions are crowded, others are strangely empty. These gaps are known as Kirkwood gaps. They occur at specific distances from the Sun where an asteroid's orbital period would form a simple ratio with Jupiter's, such as 2 or 3 orbits for every one of Jupiter's. At these resonances, Jupiter's repeated gravitational tugs destabilize asteroid orbits, gradually clearing those regions. This reveals an important truth. Asteroids are not only shaped by collisions, they are shaped by rhythm. Orbital resonance acts like a cosmic metronome, sculpting the solar system over billions of years. Not all asteroids remain safely in the main belt. Some are slowly nudged out of stable orbits by gravitational interactions, collisions, or subtle forces like the Yarkovsky effect, where sunlight causes tiny but persistent changes in motion. When this happens, asteroids can migrate inward toward the inner solar system. These objects become near-Earth asteroids, or NEAs. NEAs are defined as asteroids whose orbits bring them close to Earth's path around the Sun. They are divided into groups based on how their orbits intersect with Earth's orbit. Some cross Earth's path, some approach from outside, some remain mostly inside Earth's orbit. These asteroids are closely monitored not only because of potential impact risk, but because they are easier to reach with spacecraft. Many of the asteroids visited by missions like OSIRIS-REx and Hayabusa belong to this group. There is another, more stable population of asteroids that occupy special positions in space. These are the Trojan asteroids. Trojan asteroids share an orbit with a planet, clustering around gravitational balance points known as Lagrange points, specifically points 60 degrees ahead and behind the planet in its orbit. The largest Trojan populations belong to Jupiter, which hosts millions of these objects. They move in lockstep with the planet, maintaining stable positions over billions of years. Trojan asteroids are especially valuable scientifically. Because they have remained undisturbed for so long, they preserve pristine material from the early solar system. Other planets also host Trojans, including Mars, Neptune, and even Earth. Together, these populations reveal that asteroids are not debris drifting aimlessly. They are arranged. They occupy gravitational niches, some chaotic, some stable, some temporary. Asteroid locations tell us where gravity allows order and where it enforces chaos. And now that we know where asteroids are found, we must ask how they behave, how do they move, how do they spin, and how do they change over time. To answer that, we must examine asteroid motion itself. Asteroids may look motionless when viewed through a telescope, but in reality they are in constant motion. They orbit the Sun, they spin through space, and over long periods they change. Asteroids' orbits are governed by the same laws that control planets, gravity and momentum. Most asteroids follow elliptical paths around the Sun, influenced by the gravitational pull of nearby planets, especially Jupiter. Some orbits are stable for billions of years. Others are chaotic, slowly shifting until an asteroid is pushed into a new region of space. Even small gravitational nudges can matter. Over millions of years, these tiny influences accumulate, altering an asteroid's path. Asteroids also rotate. Unlike planets, many asteroids rotate irregularly. Their shapes are uneven, their mass is not evenly distributed, and their internal structure can be loose and fragmented. Some asteroids spin slowly, completing a rotation in days. Others spin rapidly, spinning once every few hours. There is a limit to how fast an asteroid can spin. If a rubble pile asteroid rotates too quickly, centrifugal forces overcome gravity, and material begins to drift away. This can lead to reshaping, surface landslides, or even the formation of small moons. Sunlight itself can change how asteroids move. This effect is subtle but powerful over time. Known as the Yarkovsky effect, it occurs because an asteroid absorbs sunlight and re-emits that energy as heat. This thermal radiation produces a tiny force that can slowly push the asteroid inward or outward in its orbit. Although extremely weak, the Yarkovsky effect can significantly alter an asteroid's trajectory over millions of years. Related to this is the Yorp effect, which changes an asteroid's rotation. As sunlight reflects and radiates unevenly from an irregular surface, it can gradually speed up or slow down an asteroid's spin and even tilt its axis. These effects help explain why some asteroids spin unusually fast or display strange shapes. Collisions also play a central role in asteroid evolution. Throughout the solar system's history, asteroids have collided repeatedly. Some collisions gently merge bodies, others shatter them completely. When large asteroids break apart, they form asteroid families. groups of objects that share similar orbits and compositions, tracing back to a common parent body. These families provide a record of ancient impacts. Asteroids are not static relics, they are dynamic participants in an ongoing process. Their orbits shift, their spins evolve, their surfaces weather under constant exposure to radiation and micrometeorite impacts. Over time, space slowly reshapes them. Understanding asteroid motion is essential. It tells us where asteroids came from, where they are going, and whether any might someday intersect with Earth. And that leads us to a crucial comparison. Asteroids are often confused with comets and meteors, but they are not the same. To truly understand asteroids, we must distinguish them from other small bodies in the solar system. When people look up at the night sky and see a streak of light or hear about a rock moving through space, the terms asteroid, comet, and meteor are often used interchangeably. Scientifically, they are very different. Understanding these differences is essential to understanding how the solar system works. Let us begin with asteroids. Asteroids are primarily rocky or metallic bodies that orbit the Sun. Most are found in the inner solar system, especially in the region between Mars and Jupiter. They are generally inactive, meaning they do not release gas or dust. Asteroids are ancient, stable, and relatively unchanged. Now compare this with comets. Comets form far from the Sun, in cold regions like the Kuiper Belt and the distant Oort cloud. They are made of ice, dust, and frozen gases, often described as dirty snowballs. When a comet approaches the Sun, heat causes its ices to sublimate, releasing gas and dust, creating a glowing coma and long tails that always point away from the Sun. Asteroids do not behave this way. But the boundary is not absolute. Some objects blur the line, showing both rocky composition and weak comet-like activity. These are known as active asteroids or main belt comets. This reminds us that nature rarely fits into perfect categories. Next are meteoroids. A meteoroid is a small fragment, often a piece of an asteroid or comet, traveling through space. These fragments range in size from grains of sand to boulders. When a meteoroid enters Earth's atmosphere, friction heats it rapidly. The glowing streak of light we see is called a meteor. Most meteors burn up completely. If any fragment survives the journey and reaches the ground, it becomes a meteorite. Meteor showers occur when Earth passes through streams of debris left behind by comets or sometimes asteroids. Famous meteor showers like the Perseids and Leonids are reminders that Earth moves through a dynamic environment filled with debris. Although asteroid impacts are far less frequent than meteors, their consequences are far greater. A small meteor produces a momentary flash. A large asteroid can reshape life on Earth. Understanding these differences helps scientists track risk, origin, and behavior. Asteroids are solid, comets are icy, meteors are events, not objects. Each represents a different stage of solar system material interacting with Earth. And now, having distinguished these bodies, we arrive at a more serious topic. Asteroids are not only scientific treasures, they are also potential threats. To understand that risk and Earth's long history with impacts, we must examine the role asteroids have played in shaping our planet. Earth has never been isolated from space. From the moment our planet formed, it has been shaped again and again by impacts. In the early solar system, collisions were common. The young Earth was bombarded by asteroids and other debris, a period known as the Late Heavy Bombardment. During this time, impacts reshaped the surface, delivered materials, and influenced the conditions under which life would eventually emerge. Today, most of those scars are gone. Earth is geologically active. Erosion, plate tectonics, and weather erase impact craters over time. But the record still exists in ancient rocks, in the moon's surface, and in the history of life itself. One impact stands above all others in public awareness. 66 million years ago, a large asteroid struck what is now the Yucatan Peninsula. The impact created the Chicxulub crater, more than 180 kilometers wide. The energy released was beyond anything humanity has ever experienced. Within minutes, shock waves circled the planet. Within hours, wildfires ignited across continents. Within days, dust and aerosols filled the atmosphere, blocking sunlight. Global temperatures dropped, photosynthesis collapsed, food chains broke apart. The dinosaurs did not vanish overnight, but the impact triggered a mass extinction that wiped out approximately 75% of Earth's species. This permanently reshaped the course of evolution. Asteroids are not just destroyers. Earlier in Earth's history, smaller impacts may have delivered water and organic compounds, ingredients essential for life. Creation and destruction are intertwined. In the modern era, large impacts are rare, but they are not impossible. Scientists estimate that asteroid impacts large enough to cause global damage occur every tens of millions of years. Smaller regional impacts occur more frequently. To assess risk, scientists track near-Earth asteroids and calculate their orbits far into the future. Potential hazards are evaluated using scales such as the Torino scale, which communicates both the probability and potential consequences of an impact. Despite dramatic portrayals in movies, most known asteroids pose no immediate threat, but monitoring continues, because even a small chance becomes significant when the consequences are global. This is why asteroid research is not just academic, it is planetary defense. Understanding asteroid composition, structure, and motion allows scientists to plan mitigation strategies, from early detection to possible deflection. Asteroids remind us of vulnerability, but they also remind us of responsibility. For the first time in Earth's history, a species exists that can detect and potentially prevent a cosmic impact. That is a profound shift, and it leads us naturally to the question of how we study asteroids in detail, not just from Earth, but up close. To understand asteroids fully, scientists have sent spacecraft to meet them face to face. For centuries, asteroids were little more than points of light in telescopes. Today, we study them up close. Understanding asteroids requires more than observation. It requires direct interaction, flying past them, orbiting them, landing on them, and even bringing pieces of them back to Earth. The first step in asteroid study begins on the ground. Astronomers use optical telescopes to track asteroid positions and brightness. By measuring how an asteroid's light changes over time, known as a light curve, scientists can determine its rotation rate, shape, and even the presence of moons. Radar observations take this further. By bouncing radio waves off nearby asteroids, scientists can create detailed 3D models, revealing surface features, spin states, and orbital precision. But the most transformative insights come from space missions. One of the earliest asteroid missions was Near Shoemaker, which orbited and later landed on asteroid Eros. It revealed a heavily cratered surface shaped by billions of years of impacts. The Dawn mission explored two very different bodies, Vesta and Ceres. Vesta showed evidence of volcanic activity and differentiation, while Ceres revealed water-rich minerals and subsurface ice. These findings challenged simple definitions of asteroids and blurred the line between asteroids and dwarf planets. Japan's Hayabusa and Hayabusa 2 missions achieved something extraordinary. They landed on asteroids, collected samples, and returned them safely to Earth. These samples allowed scientists to analyze asteroid material in laboratories with unprecedented precision. NASA's OSIRIS-REx mission did the same with asteroid Bennu, delivering pristine samples that contain organic compounds and hydrated minerals. These sample return missions are revolutionary. They allow scientists to analyze asteroid material without the limitations of remote sensing, revealing isotopic compositions, mineral structures, and chemical histories. Asteroids have also been used for experimentation. The DART mission intentionally collided with a small asteroid moon to test whether kinetic impact could alter its orbit. The mission succeeded, proving that asteroid deflection is possible. This was not science fiction, it was a controlled experiment in planetary defense. Together, these missions have transformed asteroids from distant hazards into accessible scientific targets. They have shown us that asteroids are complex worlds, shaped by heat, water, impacts, and time. But the story does not end with understanding. Asteroids may also shape humanity's future. They contain resources. They offer strategic locations. They may support exploration beyond Earth. To explore that possibility, we turn to the future. For most of history, asteroids were seen only as threats, objects to fear, objects to avoid. But as our understanding deepened, a new perspective emerged. Asteroids are not just dangers drifting through space, they are resources, and they are challenges that humanity may now be capable of addressing. Let us begin with resources. Many asteroids contain materials that are rare or difficult to access on Earth. Some are rich in iron, nickel, cobalt, and platinum group metals. Others contain water locked inside minerals or ice. Water in space is not just for drinking, it can be split into hydrogen and oxygen to create rocket fuel. It can be used for life support. It can shield astronauts from radiation. In this sense, asteroids represent potential fuel stations and construction sites for future space exploration. Mining asteroids would not be about bringing materials back to Earth, at least not at first. The real value lies in using these materials in space, reducing the need to launch everything from Earth's deep gravity well. However, asteroid mining is not easy. Asteroids have almost no gravity. Anchoring equipment is difficult. Extracting materials requires technologies that are still being developed. For now, asteroid mining remains a long-term possibility rather than an immediate reality. But planetary defense is no longer theoretical. Detecting asteroids that could impact Earth is an ongoing global effort. Space-based telescopes and automated surveys constantly scan the sky for near-Earth objects. Once detected, scientists calculate orbits far into the future, identifying potential risks decades or even centuries in advance. Deflection strategies depend on knowing an asteroid's structure. A solid rock behaves differently from a rebel pile. One tested method is the kinetic impactor, striking an asteroid with a spacecraft to change its orbit slightly. Over time, even a small change can cause a miss instead of a collision. Another proposed method is the gravity tractor. A spacecraft would hover near an asteroid, using its own gravity to slowly tug the asteroid into a new trajectory. Other ideas include altering surface reflectivity to enhance solar pressure, or using focused energy to create controlled outgassing. What matters most is early detection. The earlier an asteroid is found, the more options we have. Planetary defense is not about last-minute heroism. It's about patience, precision, and preparation. Asteroids force humanity to confront a unique responsibility. For the first time, a species can protect an entire planet from a natural cosmic disaster. That is not just a scientific achievement, it's a moral one. And yet, asteroids are not only about the future, they are also about the past and about meaning. To understand why asteroids matter so deeply, we must step back one final time and look at the big picture. We have followed asteroids from their birth in the earliest days of the solar system to their role in shaping Earth's past and humanity's future. Now we step back, because asteroids are not just objects in space, they are storytellers. Asteroids preserve time in a way few other objects can. While planets evolve, melt, and erase their early histories, asteroids remain mostly unchanged. They are geological fossils, drifting quietly through space. When we study asteroids, we are studying the original materials from which planets were built. We are reading a record written before Earth existed. Asteroids also help explain one of the most profound questions in science. How did life begin? Many asteroids contain water-bearing minerals and complex organic molecules. Some meteorites contain amino acids, the building blocks of life. These discoveries suggest that asteroids may have delivered critical ingredients to the early Earth, enriching a young planet already capable of chemistry. Asteroids did not create life, but they may have helped prepare the environment in which life could emerge. They also shaped evolution through destruction. Mass extinctions caused by impacts reset the biological clock. Entire ecosystems vanished, making space for new forms of life. The rise of mammals, and eventually humans, is directly tied to an asteroid impact. In this way, asteroids are both creators and destroyers. They embody the balance between chaos and order. Asteroids also teach us humility. They remind us that Earth exists within a dynamic cosmic environment. Space is not empty, it is active. Collisions are rare, but they are part of the natural rhythm of the universe. What makes this moment in history unique is awareness. For the first time, we can see asteroids coming. We can understand their motion, and we may be able to change their paths. That is not power over nature, it is participation. Asteroids are not enemies, they are remnants of creation, still moving through the architecture of the solar system. Every atom in our bodies was once part of ancient cosmic material, forged in stars, assembled into dust, and shaped into worlds. In that sense, we are made of asteroid material. When we look at an asteroid, we are looking at ourselves, reflected across billions of years of time. Asteroids remind us that creation is ongoing. The solar system is not finished, and our story within it is still being written. That is why asteroids matter. Not because they might one day hit us, but because they reveal where we came from, what shaped us, and what responsibility we now carry. They are the quiet witnesses of cosmic history, and they are still watching. As we come to the end of this journey, take a moment to let the silence return. The asteroids are still out there, moving quietly, following paths written long before we were born. If this exploration helped you see the universe a little differently, you can support this channel in a simple way. You can like this video. It quietly tells the algorithm that curiosity still matters. You can subscribe so future journeys through science and the cosmos can find you. And if you feel like it, share this with someone who enjoys slowing down and looking deeper. Before you go, I'd love to hear from you. Where are you watching from right now, and have you seen asteroids? You can leave your thoughts in the comments below. Until next time, keep looking up, keep asking questions, and remember, the universe is still speaking.